we may start from 2 o'clock.
Okay, now yes, is data-driven control and identification.
Right, very good, very good. That's
Yes.
I want to make sure. So we'll start at 2. That's okay. It's about 10 more minutes, right?
Yeah, we may start on time.
Okay, no problem. So just let me know if it's not showing up. I'll have to stop share and again share. Hopefully you'll see that time. But for the moment, I think everything's okay.
How can I say? Host is the Gopal, right?
After me, it's Dr. Gopal.
Chair is Gopal, isn't it? No.
No, I thought it was Dr. Subrahmanyam.
Not the Gopal. Who is the chair?
Dr. Subrahmanyam is what the program you sent me said.
Yes. Prof. Viswanath is now going to give a keynote address 1, and Prof. Subrahmanyam is the chair of this keynote session.
Yeah, it's Subrahmanyam.
Yes.
Right.
Is he available?
I don't, as of yet, it doesn't show him as one of the participants.
He is not available. Any person is okay. I mean,
yeah, don't bother with the introductions and all that. That's just formalities. It's okay. Okay. So if Dr. PVS is not here, and you want me to start immediately, I'll do so.
Viswanath is originally a student of Professor Subrahmanyam. He is the supervisor. So
no, he was not my supervisor. He was just my teacher at IIT Madras.
Okay.
I didn't do my dissertation with him, no. But he knows me very well.
When Professor Subrahmanyam will not be available, please let me know. I'll take care of chair.
Okay.
So I prepared his abstract.
Mm-hmm. Dr. Tan, I've been to Malaysia before, and it's a wonderful place, especially for eating.
I see. Glad. So, Prof, may I know when you visited? In what year you visited Malaysia?
Okay, 2010. I
2010.
I went to Singapore in 2008, and I really liked the food there. And people said you have to go to Malaysia; it's even better.
I
So
see.
yeah.
So which city you visited in
I
Malaysia?
visited lots of places there. I went, of course, Kuala Lumpur. I
see.
went to Penang.
Yeah.
I went to this very famous national park. Its name is just National Park. I don't remember. It's in the middle of the country.
Yes, yes. It's a middle of the Peninsula Malaysia. It's a it's a deep forest.
Yes. What's the name of
deep
it?
forest. It's a national park. But in Bahasa, in Malay language, it is a Taman Negara.
Right, Taman Negara. That's exactly what I went.
Taman Negara. So it's exactly the name that you spell that you mentioned in English, but we just make it a specific name. Yeah. So glad to
Then I
hear
went
that you
to
have a good
Sarawak.
experience here.
I went to Sarawak.
I see. So I think for information, there are some changes over the 10 years. I hope that you may visit again.
Sure. There's lots of beautiful places there which I'd like to go to. I would like to go to Sabah.
Sabah also. If you like diving, I think definitely this is a good place for diving, and also sandy beaches.
Right. I came to Sarawak for that enormous flower, which flowers once in every, I don't remember, 12 years or something.
Is it very big in size?
Yeah, enormous flower.
We call it the Rafflesia. Rafflesia.
Rafflesia, exactly, Rafflesia.
Yeah, Rafflesia. It could be quite smelly.
Yeah, I've heard about it. It didn't happen. When I came there, it was supposed to be the time for that, but it never happened.
I see. Hope you have the chances.
No, next time I have to come and see it again.
Yeah, make a trip.
Yeah.
Make a trip to Kuching and Sarawak.
Yeah,
but it is at the East Malaysia. I'm now in the West Malaysia, Peninsula Malaysia.
I see. Okay.
Yeah. So
it's a beautiful, beautiful country.
Yeah, welcome again to visit. And then, by the way, how's the weather there? Very cold?
In Dallas today, it's actually sort of warm, but it's been getting cold. I mean, just a few days ago, we had temperatures between 0 centigrade and 10.
That's considered.
Today it's almost 20.
20 in the daytime. All right. I think they're still fine, but let's say in the nighttime could be cooler.
Right. But it's not terribly, I mean, it's not bad today.
I see.
You can get by with just a jacket.
Okay. Okay. So it's now holidays, right? It's not holidays over there, right?
Yeah.
Until end of this year?
No, actually, we were supposed to start on January 10th, but because of this uncertainty, because of Omicron, it's been pushed back to January 18th. So we don't know what will happen. So I certainly have holidays till January 18th.
Oh, so from now on until January 18th. I see. So it's a holidays over here, but my campus, the school will start 2nd of January. It's a new trimester. It's a new trimester in another it's a 2nd trimester in academic year. Yeah.
Wow. Which city are you in Malaysia?
I'm from Malacca.
That's the other city I wanted to go to, Malacca. I heard that there were 4 major ports: Kuala Lumpur, Singapore, Malacca, and Penang, right?
Yes, but this is history. Over the years, Malacca is no longer one of the main ports in Malaysia. It's actually right now it is a historical city. We have port, but it's not for let's say
commercial purposes.
No, what I mean here is it's a port. There is a port, but there is port for oil and gas only. It's not for like what you say commercial. Right? It's not for goods. It's not for goods. It's not for goods.
I see. Okay.
I see. Then this is small town. The small town, and then but full of history. Again, there are a lot of good food here.
I know that if Malaysian food and Singapore food is the best on earth.
Really?
Yeah, I think so. Yeah.
Glad to hear
You
that you
have
enjoy
an
food
enormous
there.
variety of people.
Professor.
Yes, yes, I think that we have yes, we have fellow Indians, Chinese,
Mhm,
and also
mhm,
Malay. Yeah.
mhm,
Of course, others people from other nationalities are also in this city.
mhm.
Yeah.
Shall we start now?
So it's almost 11. Yeah, let's start. Can you all hear me?
Yes, yes.
2 o'clock in Japan time.
Oh,
Do you
wait.
like to start?
Yeah, I can start if you don't mind.
Okay. So the may I be chair now?
Sure, sure, no problem.
Okay. The next is the keynote. First keynote. The title is Data-Driven Identification and Control, an overview by Professor Viswanath Ramakrishna. So I introduced him briefly. So he obtained his education at St. Stephen College, University of Delhi, the Indian Institute of Technology, Madras, and Washington University in St. Louis. He obtained his doctoral degree in 1991. He has been with the University of Texas at Dallas since 1995 with stint. What does this mean? At the University of
Short appointments.
Okay, at Davis and Princeton University. Quite a good career. His research interests are in control and identification, especially of nonlinear and quantum system. The photonic signal processing, the Clifford algebra, and data-driven identification of system. Today's topic is on data-driven identification system. So welcome Professor Viswanath Ramakrishna.
Thank you so much. Yeah, thank you so much, Dr. Watada, and thank you for inviting me, and I thank all the organizers.
Anytime.
Those of you who are in Malaysia, in Korea, in Japan, etc., and China, thanks for doing this. It's a difficult time of the year, difficult time in our lives with this Omicron and all that, but still, it's great to be able to meet together. So this first page is going to be about some depths of gratitude that I want to sort of make explicit over here. I've already said thanks to you, Dr. Watada, and your collaborators. I would like to thank Dr. PVS. It was he who introduced me to the world of FIM, Forum for Interdisciplinary Mathematics. It has been very, very nice to me to be part of this community of mathematicians and people who apply mathematics. I would also like to give a great debt of acknowledgement to Professor Bhudev Sharma. I've known him only for 2 years, from let's say middle of 2019. We heard early today morning from Dr. PVS and others, as we know that he's a top-rate mathematician, a consummate professional. But what is the most important thing about him was that he was very kind, and this is what we should all aspire to be. It was, for me personally, very flattering that someone this important, at least in the world of Indian mathematics, and certainly also internationally, was so nice to me without any airs. He was just genuinely down to earth. All right, keeping on in the theme of great debts, you see here, I say with collaboration of Alain Bensoussan. In reality, he was the driving force for the portion of the research of ours that I'm going to present today. Alain Bensoussan is well into his 80s, but he is still very active. He is a legend in the field of systems controls and PDs and a variety of variational inequalities. And it's amazing how alert and agile he is, and also very kind, just as Professor Bhudev Sharma. The remaining collaborators here, Dr. Minben Tran of SMU, Southern Methodist University, which is also a major university in Dallas, and Dr. Fatih Galir, he's my student and Dr. Bensoussan's student. He just graduated last Friday, and he's working at Welltower, which is a medical health consulting firm. All right, so what am I going to talk about today? I'm going to give you some sort of an overview of data-driven control and identification. Initially, I just had an overview in the title, but I decided to make it idiosyncratic because obviously it's impossible to give a complete overview of such a burgeoning field. So I've decided to make certain idiosyncratic choices, okay? And those are in the next page. So what I'm going to discuss today is recent results on what's called sample complexity of the linear quadratic Gaussian regulator in the presence of noise. Then this is work of Sarah Dean, Matney, Nikolai Matney, Hu, Benjamin Recht, and a variety of other people. I think I have the full list when I start this particular thing. Then I'm going to talk about a notion called persistence of excitation for data-driven control. This is the work of Dippersis, etc. And both of these things give you an estimate on the number of measurements you should make, but in different ways, okay, to achieve identification essentially. I'm going to do something which is controllability and the notion of expressivity of neural networks. We'll show that under very mild assumptions, you have to train just about 5 parameters in a deep neural network for it to be a universal interpolator, not necessarily a universal approximator. And then finally, I will talk about identification of linear control systems. This is our work. The novelty here is we assume that the state is only seen through measurements. So the fact that we can only access the state through measurements creates a few problems, and we'll discuss what are the hurdles and obstacles that one has to overcome. All right, so obviously it would be remiss of me not to mention the various other interactions with control and machine learning. You know, after all, this is the age of data, so we are told. Everyone wants to get on the bandwagon, but of course, saying it more charitably, there's always been a long interaction between notions in control theory, namely system identification, that's very, very close in relation to machine learning, for instance. The principal difference was prior to the current era, the results in system identification were asymptotic. That is, you let the number of measurements go to infinity and say you obtain good identification. And nowadays, people are using a finite amount of data to see and say what they can achieve. Here are some more areas of interaction. There's a deep interaction with dynamic programming, which is an area within controls, and what's called reinforcement learning and control. There's even a book on it by Dimitri Bertseikas. There's a recent review about on it, a very comprehensive review by Benjamin Recht. Then there is very important work of Weinan A and his collaborators, Osher, etc., and UCLA on the relationship between deep neural networks and what's called the maximum principle. I'll get to that when I talk about controllability and expressivity. Then there's an area called mean field games and control. It'll be too difficult for me to explain what that is briefly. And there is an obvious connection in the sense that mean field games and control are the appropriate thing when you want to generalize the stochastic gradient, when you have, let's say in the limit of infinite number of layers, okay? Then there is, of course, work long before in the 90s and early 2000s on the relation between controllability and recurrent neural networks due to Sontag and Sussman. And of course, I could go on and on in this, and I'm not even qualified to talk about the vast majority of these things, so I will not talk any further about these things. All right, so the first result I want to discuss is this result on sample complexity of the linear quadratic Gaussian regulator. This is your Saradine, Mania, Matney, Recht, and 2. And this is a sample complexity result which is reminiscent of probably approximately correct. And the idea is you're given some sort of a probability of error, and you want to minimize, let that enter as a parameter, and you say how many measurements you need to make. So let me be a little bit more precise. So what this paper considers is a discrete time linear system. Xt plus 1 is axt plus but plus wt. Use a control which is assumed to have some noise. Wt has noise already. This is called the process noise. You don't know a and b, okay? A and b you do not know. And the goal is to minimize the expectation of this quantity over here. Q and R are positive definite matrices. But this is a bit of a red herring in the sense that what they really do is consider what's called the infinite horizon linear quadratic regulator problem. And the way they do it is take a finite number of measurements, but I'll get to it in a minute. Repeat those measurements with obviously different realizations of these noises, and then give a bound on the number of those repetitions. Okay, so I emphasize that the result is we do not know A and B. In the infinite horizon case, if you knew A and B, there is an explicit solution to this problem, the linear quadratic regulator. In the finite horizon case, there are still constructive procedures based on dynamic programming, okay? So the idea, what they do, therefore, really is an identification plus control result. So you use number of measurements, a certain number, you estimate A and B, do some control on it through a certain technique, and then estimate how far that is away from the optimal performance on the true A and B. The assumption in this example, and in fact, all the three examples of linear control system that I have, is that indeed the data comes from a genuine linear system, okay? So this is your hypothesis class in the language of pack learning, okay? All right, so what they do here is first define these two matrices. A GT is AT minus 1B, followed by AT to the minus B, all the way up to AB and then B. And FT is AT minus 1, AT minus 2, and I. That is, if you chose B as identity, then this would be the case. Incidentally, the dimension of the controls is not necessarily the same as the dimension of the state, okay? So these are just two matrices which are well known in the controls community, called the finite time controllability gradient for control and the noise. So this is the noise part, this is the control part. All right, so what does the theorem say? So let me first tell you how the A and B are estimated. So what you do, you always initialize your state at the origin. Measurements, right? T steps, that's called a rollout. And you repeat this process of collecting XTs and UTs capital N times. So the estimate is on how large N should be, this N, okay? So this N is not the same as normal. So first and foremost, we assume that UT is normal with mean 0, variance sigma U squared times high P. So this is a positive constant. And likewise, the noise is also mean 0, but sigma W squared times IN. And this parameter is the same as what you would see in a pack learning result, right? So you're given a probability of not getting the thing right, and you want to minimize that. And what you do then is to collect samples. This should have been a capital T. I apologize for that. And you will see later on what you really do is, even though you collect this T measurements, you only use the last step. And that's for a purely technical reason. Okay, and I'll get to why that is later. And the result now says the following. So let n be bigger than or equal to 8 times n plus p. N here is the dimension of x, p is the dimension of u, plus 16 times log 4 by delta. So if delta is very, very small, this gets large. And likewise, of course, there is a dependence on n plus p. Then with probability at least 1 minus delta, when using only the final sample of the trajectory, the least squares estimate of A and B, and I'll tell you what the least squares estimate is in a minute, A hat, B hat, deviates from the true A by this quantity. So this is C is this, I could not fit it in one line in the transparency, that's why I put it separately. So it is n plus 2p log 36 by delta divided by n, 16 times sigma w. I remind you, sigma w shows up here. And then the smallest eigenvalue of the positive definite matrix, sigma u square gt gt transpose, sigma w square ft ft transpose, it's reciprocal. Okay. And then b minus b hat does not depend on the smallest eigenvalue. Okay. So the estimate only, so these are spectral norms. Okay, by the way, these are spectral norms. That is what's sometimes written as the 2 norm. So this is your estimate. Okay. Of course, there is a big problem in a certain sense, naively using this result, because we don't know the true A and B. So if we don't know the true A and B, we don't know GT, we don't know FT, and therefore we cannot estimate this. In their paper, they argue that using a certain bootstrap argument, they can get an upper bound on these quantities, which may well be a conservative estimate. Okay. So let me now go, is this 4? This must be 5. Okay, so that's what I've written over here. Only A minus A hat involves the unknown quantities, whereas B minus B hat doesn't. And now what is the least squares estimate? You see here, what you choose A hat, B hat as the minimizer of A xt minus 1 plus B u t minus 1 minus x capital T length square. That's what I mean by using only the final sample of the collection. And of course, you do it for all capital N times. And each time for each L going from 1 to N, you always initialize as 0. Okay. All right. Now, what they further do, and I will, so this is also very fairly complicated here. So part of the reason for them to study the infinite horizon case is, of course, there's a well-known solution, which I mentioned before, which is what I call the J. Riccati. So there is a, so this is the minimum cost of the linear quadratic regulator for on the true A and B using the K designed on the nominal A hat B hat, right? And to compare it with what would be the deviation, you measure J. Riccati, that is I mean, if you knew A and B, you do your standard linear quadratic regulator, you'd find the K using a Riccati equation and you'll compute the minimal cost. That thing is bounded by some universal constant here, C0. And to be honest with you, I got a little lost in trying to follow what this universal constant is, but obviously because it's universal, doesn't depend on it doesn't depend on sigma W, sigma U, etc. And certainly not on the specifics of the things. This R is the resolvent of A plus BK. So remember, if those of you know about the linear quadratic regulator, there is a feedback gain matrix, A plus BK, that K. So R is A plus BK. It's H infinity norm divided by 1 over square root lambda G plus a few other things. This estimate holds with probability 1 minus delta if, in addition to N satisfying the assumptions before, it's larger than this. So this is a typical sample complexity result. The only problem with it is, of course, it looks like it's a bit wasteful in the sense that even though you collect x0, x1, xt minus 1, u0, u1, ut minus 1, you're only using the last step. And this is for a purely technical reason. For those of you who are familiar with pack learning, you do know that many of the results in it are proved through what are called concentration or measure inequalities or large deviations inequalities. And those results are proved under certain independence assumptions. And if you use the full measurements, the independence assumptions would not be met. And so in a certain sense, it's wasteful. And now there's a lot of effort being put into trying to see how much you can salvage if indeed you used everything. Okay, so this is the first result that I wanted to discuss. Okay, so this is these things have now been published. Okay, so here's some more information. R is the resolve under A plus BK, and K is designed by a technique called systems level synthesis. It's a rigorous technique on the estimated A hat B hat. Okay, so you found A hat B hat through that least squares calculation, and then you do something called system level synthesis, whatever that may be. It gives you a K, and then you compare it with what you would have had you had the actual A and B. That's J. Riccati. Okay. All right, so the next result I want to discuss is slightly different. So in the previous result, I gave you what you're guaranteed if N is at least so much, capital N. But I never made any mention of about what T should be. Okay, how many measurements you should collect in what's called a single rollout experiment. So the next set of results addresses that, but they don't assume noise. In fairness, their paper addresses disturbances which are bounded. So you have a true system, true dynamics plus a disturbance, and you have an upper bound on its norm. Okay. So it's not that bad, but it's not a stochastic result. Okay, so though there are people now trying to work on extending these things. So for that purpose, we need to briefly go through the notion of a persistently exciting signal. So loosely speaking, it is a signal which manages to excite all the modes, all the important modes. So remember, we had something like that in the previous result too. Because this, let me just go back here, this quantity here, this lambda square, this really is a measure of how much energy you have to put into the control to generate, to excite its least excitable mode. So the system is controllable, that is implicit in the assumption that this thing is not zero, but this is a quantitative measure of how difficult it is to estimate to excite that most closest to uncontrollable mode. So in a similar sense, but not exactly identical, this is also some such thing. So for the moment, this is something purely about a vector valued signal. So zk for each integer k is a vector of length sigma, and we collect z0, z1, zt minus 1, whatever that may be. That is said to be persistently exciting of order L in the following matrix. So remember, this is a Bloch-Hankel matrix. So these are vectors, Z1, this is also Z1, and then it goes on like this. This should have full rank sigma L. So necessarily, but not sufficient, the T must satisfy this inequality that I have over here. I should say that this notion is an old one in system identification and adaptive control, which, by the way, is also now going through a great renaissance in conjunction with machine learning. So, of course, there are various versions of this notion adapted to the applications in mind, but essentially they have the same, let's say, the same moral impulse. You want to excite the least, how much you must put in by way of energy to get what you want. Okay, so that is what, so it's persistently exciting if you can do what it takes, loosely speaking. Let's leave it at that. So this was then honed into what's sometimes called the behavioral framework for control systems by Jan Willems and his collaborators. And then it was resuscitated most recently in the state space setting, which is a normal setting for control systems, for data-driven control by De Persis and Tesi. And now, if any of you is interested, there's a very good thesis by Henk van der Waarde from, obviously from the Netherlands, but I don't know where exactly, I've forgotten. They've got a very famous controlled systems group. His thesis goes into what all you can do with this notion and what can be salvaged if your signal is not persistently excited. Anyway, so now you consider a control system, xk plus 1 is axk plus buk. We don't assume any stochastic noise, but as I said before, that paper contains situations where you also have a plus dk, where dk you have some sort of a upper bound on its norm. We'll now assume that the signal u0, u1, ut minus 1 is persistently exciting of order n plus 1. So now I've decided not to, I've used the same notation for the dimension of state and control as the authors of these papers did. So n is the dimension of x, um is the dimension of u for this particular segment of my talk. So in particular, t must be larger than this number for it to be persistently exciting. But of course, just being larger than this is not enough. You need a certain full rank condition. An important consequence of this is if you collect UD0, so our assumption is, so let me first explain what this subscript D means. The subscript D means data. So you feed it with some controls. You have complete control over what you feed it. Of course, the state evolves. Once again, we're assuming that there is in fact a true system. And the D just represents our measurements of the state in response to the signal. So we're going to assume that the top row is persistently exciting of order n plus 1. And an important consequence of this is that this matrix has got full rank n plus m. And more importantly, any other input state trajectory corresponding to the true system, which we assume exists, would be a linear combination of the columns of these things. Okay, so as a consequence of this, the state dynamics can be rewritten as xk plus 1 is x1 capital T, where x1 capital T is xd1. So here you start at 0, go up to t minus 1. Here you start at 1, go up to t. Again, data, right? The same thing. You collect at stage t as well. This is any right inverse of this full rank matrix, right? So this is surjective, this linear map. So it has a right inverse. And you can write xk plus 1 in this fashion. Okay, and the proof, this is also an identification result, but I will explain it in a way which is, it's not identification and then control. You can do control directly, but let me get to that in a minute. What the proof actually shows that the true pair AB, BA written this way because of U and X being written this way, equals this quantity, X1T R sharp dagger, which is this this quantity here, and it's the minimizer of x1t minus ba r0td Frobenius norm. That is sum of all the entries square of a matrix taken square root. Okay. All right. So as I said, the foregoing is an identification result. You might say, so they're not really doing direct control. That is, you take the data and directly design your feedback. They're finding that an A and a B, which is very close to the original A and B, doing design on the, but in fact, that's not so. To understand this, what you must understand is practically all control problems for linear state space systems. What you're doing is designing what's called a feedback matrix, feedback gain, so that A plus BK has some desired behavior. It could be that it's all its eigenvalues are on the unit disk, or other more exotic requirements. The point is, regardless of what your gain is, the closed loop system A plus BK equals x1t times gk. This is pure algebra, where you can write kin as r0td times gk. So this matrix gk, which appears here, is the solution of this. And this has a solution because of the full rank assumption. All right. So in particular, if you wanted to find a K, for instance, which would stabilize this, is to say this is the minimal requirement that you have in any feedback design problem, that can be recast as solving what's called a linear matrix inequality. So let me, there are systematic methods of solving these things. So what you do is you take your x0t, x1t, and q is the thing you're solving for. And so you look at this matrix, this is visibly symmetric. This matrix, you want it to be positive definite, right? So once you found your q, then your k is given by this explicit formula, okay? So therefore, in fact, you don't have to, if you're only interested in feedback design, you don't need to find the A and the B according to the previous page. You can use the data that you generated and directly find your feedback design, feedback controller, okay? So this is now a fairly vibrant area of the interaction between control theory and, well, let's call it machine learning for lack of a better word, okay? So persistency of excitation has now been realized to be a very useful notion in of itself. Okay, now I want to discuss a completely different application, but it's also got to do with control, but this time of nonlinear systems. So this is work due to Cusciero, Larson, and Teichmann. And so first, if you remember in the second page, I'd already talked about the works of Viswanath, etc. So let me briefly tell you what is the viewpoint in that field. So these things are sometimes called neural ordinary differential equations, which is just a fancy name. So what it is you take a deep neural network, but the parameter k, which counts the number of layers in a deep neural network, of course, k will be very large, you essentially replace it by a continuous parameter. So in other words, very informally speaking, you view the original deep neural network as a time discretization of this differential equation. And the parameters of the neural network, which you want to train, update using whatever method you want, are represented by this theta. And this capital X represents what you feed into the input layer, right? So the assumption in this paper, and they go into some length into justifying why that this is not a huge assumption, is that your Vx theta can be written in this form. So just as optimization plays a role in supervised learning, optimal control or control theory more generally plays a role in deep learning. Again, I hate to use these fancy buzzwords. Everyone uses them nowadays, but that is the general philosophical viewpoint. So what you have is some of the parameters are in U1, U2, UD are scalar, okay? V1, V2, Vd are vector fields, so they are vectors of size m. Okay, so again, I've decided to use the same notation for the dimensions of x, u, etc., as the original paper did. So I'm sorry for that, but this is now my xt's and rm. So the assumption is you can always write it this way. So then, doing whatever task you wish, if you have control over, in other words, if you can generate any V1, V2, Vd you want, so what you would like is D should be small. That means the number, why is that? Because the number of parameters that you have to train and update would then be small, okay? So minimal D implies ease of training, right? So so these authors in their paper consider what's called a property called universal interpolation. This is different and weaker than universal approximation results that you may be familiar with. What you want is any finite subset, xi, yi going from 1 to capital N, regardless of n, as long as it's finite, of your set omega cross omega, where omega is the domain from which the x's come. So xt is contained in omega, which is a subset of Rm. And yi are also given to you. Of course, it makes no sense if you know basics about differential equations. You want the xi's to be distinct. Of course, that makes sense even without differential equations. But now, since these are flows, the yi's also have to be distinct. So what do we want? We want the the solution at time 1 of the differential equation initiated at x, that's the initial condition, at xi equaling the given value yi. Okay, so what they show is d equal to 5 suffices for this, and I will go over that. So what I want to point out is this is essentially a controllability result. So what they're saying, so if my Vx theta look like this, in the nonlinear control literature, we'd call it a driftless control system. They are good. So the authors of this work gave you the V1, V2, VD, V5, such that the vector field generated in this form, the right-hand sides, contain all possible polynomial vector fields. So let me be a little bit more precise. Just V1, V2, VD, of course, will not contain all polynomial vector fields. What is known from control theory is you must consider the collection of all vector fields obtained by taking what are called Lie brackets of the VI. So you do V1 bracket, V2, V1 bracket, V3, V2 bracket, V4, etc., and keep on iterating. And they show that this collection contains all polynomial vector fields. And from here, using some stuff from multivariate interpolation, they prove that a neural net with neural ODE with this property satisfies the universal interpolation problem. So the result, more precisely, you assume omega is an open and connected subset of Rm. Then d equal to 5 suffices regardless of what n is, as long as n is finite. So you give me million data points, billion data points, these 5 vector fields will do the job. Of course, the training can get very intricate, and I'll briefly talk about that in a minute. What are these vector fields? So first you choose 2 traceless matrices of size m cross m, A and B, such that A, B, and their iterated commutators generate all possible traceless matrices. Such the generic pair AB will do this, okay? So this is known due to results of Kuranishi from the 1950s, and in fact is true for any semi-simple Lie algebra, of which SLM is one example. Then you take the third vector field to be just the constant coordinate vector field, 0, 0, 0, 1. V4 is the last coordinate in X squared. That is the first coordinate of V4, and the balance is 0. And V5 is x1, x1. If your vector is x1, x2, xm, then V5 is x1 times xm, x2 times xm, xm times xm. So let's say m is 3, and I call x1 as x, y1 as x2 as y, x3 as z. Then this is x, z, yz, and z square. Okay. And the idea is A and B generates their brackets generates everything in SLM, and the Lie algebra generated together with E3 so E3 will essentially give us IM also. That's what it will do. Okay, so V3 so in other words, it will generate not just all traceless vector fields, linear vector fields, but generic every linear vector field. And then what you do finally is take the V3, V4, and V5. They together will generate all polynomial vector fields if you already have the linear vector fields. So therefore, the assumption is, the conclusion is if you have V1, V2, V3, V4, V5 in this very explicit form, then I throw in all possible Lie brackets, I'm going to get all possible polynomial vector fields. This is where they derive the results from. And then they go on to say, what if you like only all these fancy activation functions? So you see these vector fields, the neural architecture corresponding to this doesn't involve all your fancy activation functions. They show as long as the activation function is analytic, then d equal to 7 suffices, okay? So this is a typical application of controllability, different from the way Sontag and Sussman envisioned their results, which was a slightly different problem that they were considering. But now the burden of training becomes a problem of generating the U1, U2, U5. There's an elaborate literature on what's called the path planning problem for driftless control systems. So it's my guesstimate that those results will play a role. And so far, I've not seen any work on this, but the path planning results should play a role in this, okay? But of course, I should say that those results are also very difficult to obtain. So I remember this was a hot area in the late 90s because of robotics. Even when you had only 2 vector fields, which let's say generated everything, the thing was fairly complicated. But there are some very concrete algorithms. Okay, now let me discuss the result that I was involved with Professor Bensoussan, Min Tran, and Fatih Gelir. And as I said again, great debt of gratitude to Professor Bensoussan, who in his 80s still is going strong. So what is the problem that we considered? So we have xt plus 1 is axt plus bvt. I don't assume that I know anything except the initial state, okay? All the subsequent states are only seen through these measurements. C is known, V is known, A and B are not known, and our goal is to estimate A and B, okay? All right, so let me, to give you some perspective, if let's say Y was observed, X was observed, that is YT is XT, that is C is IN, this would in fact turn into an easy convex optimization problem. So I once again remind you, we are not assuming noise here, okay? We're not assuming noise. Because then we could find A and B by using this cost function. Gamma is just a parameter, half Frobenius length square of A plus B Frobenius length square. And now, as opposed to the sample complexity result that I presented before, we are using the entire trajectory. So you're minimizing xt plus 1 minus axt minus bvt length square summation. Okay, so I'm not just using the last part of the trajectory. You can, it's convex, it's quadratic, so it's very easy to do this problem. You can find this explicitly. So this is a problem worth considering only if there was noise when you observe the entire state. But if you do not observe the entire state, then this becomes a difficult problem. In fact, what the natural cost function that you would consider would be this cost function plus another parameter mu by 2 summation t going from t go from 2 to capital T yt minus cxt squared. From 2 because x1 is already known to us, okay? So this J is not convex, and as you can imagine, we cannot promise anything more than our gradient descent algorithms converge to necessary stationary points of the cost function. But this we can prove, okay? So how do we do this? We define the following variables, psi t is xt plus 1 minus axt minus bvt. So what is the idea? For a given A and B, of course, there's no good reason the true x should equal axt plus bvt, right? Because it's being generated by one particular given system, but I don't know what that is. In fact, I'm trying to estimate it. So this thing is not going to be 0 in general. So my design variables become therefore A, B, and psi, and I can rewrite my cost function in terms of this. And now this is what machine learning is for us. We are going to calculate the gradient and say when what gradient descent does for this. So to calculate the gradient, you can calculate it explicitly, but it'll be useless if you just work with A, B, and psi and didn't introduce this notion called the costate. The costate is well known in linear control theory, and in fact, it is essentially is the Lagrange multiplier, if you wish, of a certain constraint optimization problem. But here it plays a purely symbolic role, okay? So this is the Lagrange multiplier for a different optimization problem. But be that as it may, because lots is known about it, we introduce this new dynamic, so new vector of the same size as x, but this is a backward iteration, right? And with terminal condition prescribed here. Then if you do that, the expression for the gradient assumes this fairly benign form, if you wish. It's easier to work with this, okay? Therefore, a necessary condition for a pair A had to be optimal is, of course, obtained by setting these things equal to 0. This should be, this typo here, this is A hat X hat T plus B hat VT minus PT plus 1 divided by gamma. So the minus should have been over here, right next to the V. PT satisfying this equation with initial and terminal conditions given by this. Okay. And now we want to say more about what this grade. So we want to define a gradient descent using this. So those who are familiar with the gradient descent, you will use the gradient plus some parameter, etc. So I want to give you some theorems about when this converges and to what it converges. So for this, it's useful to notice that there are two functions going from 0 infinity to itself, both continuous and increasing, with the following properties: that the norm of the gradient is less than psi times evaluated at the original norm of z, and then this inner product is less than or equal to phi times z multiplied by z tilde square. And so what is the idea? The proof goes through by using the integral form of Taylor's theorem in the multivariate case. That's why we calculate these things. So the gradient descent is Zn plus 1 is Zn minus rho dgZn. Okay. And now I'm going to tell you under what conditions it converges and what happens. So first you define m, this number, which is mu divided by minimum of 1 and gamma. Remember, gamma is a certain parameter inside the cost functional, times t going from 2 to capital T is length yt squared. I've measured the yt, so I know how to measure this. And now you choose your rho to be less than this. So the functions phi and psi play a role here. I should say at this point that we can find phi and psi. It's not, we can find explicit forms for them. But we don't know that these are the optimal forms in a certain sense, because if you go through the proof, there are repeated applications of the Cauchy-Schwarz inequality, right? So depending on how optimally you use it, you'll get, how you use the Cauchy-Schwarz, you'll get different values for phi and psi. And it's conceivable that for one pair phi psi, you'll get better bounds, okay, than another pair. But be that as it may, if that is the case, if your rho, which is the usual parameter that you have in your gradient descent, is less than this, then the sequence JZn is actually decreasing. Zn stays within the ball of radius m, and the gradient, in fact, goes to 0. So you are certainly converging to a stationary point. Okay, it's non-convex. We do not know more. Okay. All right, there's a second algorithm, which in the paper is called steepest descent, which may be a bit misleading because there's nothing steep about it. However, what it comes about by writing the necessary condition dgz equal to 0 as an Euler condition and devising an algorithm for you. I should apologize now. My state now is in RD for this particular transparency. So this represents the iteration. The n plus first iterative A is given in terms of the nth iterative A and B and X, etc. in this fashion. Likewise, the n plus first iterative B is given in terms of the nth iterates in this fashion. And of course, we update X. This should have been X equal to, okay, there should be an equal to here. X and T plus 1 is A and X and T minus B and B and T, okay? Plus, and then this PT plus n plus 1 gamma. And then here are the terminal conditions, the P's and the X, and you can initialize the A and B as and where you please. Okay, so as long as rho is bigger than or equal to 0, then you're guaranteed that the cost function is monotone decreasing. The sequences A n, B n, X n, rho Pn are bounded, but we can't say that they go to anything. However, an plus 1 minus an goes to 0, bn plus 1 minus bn goes to 0. From there, you can show that the limits of convergent subsequences of these four quantities converge, in fact, to stationary points of the cost function. So this is what we can prove. Now, in the paper, we also have how to update. So supposing you change capital T, the number of measurements you have, do you have to redo the work? We show show through a lot of intricate calculations, thanks to Professor Ben-Susan, how to update the A and the B you found using measurements up to capital T when you use measurements up to capital T plus 1, and lots more. So what we notice is that for certain choices of the inputs, we in fact converge to the true A and B. And I suspect that this has got to do with the persistence of excitation condition that we had before. Okay. So in the scalar case, we almost always seem to converge. So that is, if my dimension X was a scalar, then we always converge. For other things, sometimes we don't go anywhere close to the original A and B, even though we're going to stationary points of this cost function. But in some cases we do, and this probably has to do with the persistence of excitation condition. All right, so lots of things are open still in this work. For instance, one thing that I've not seen addressed in a serious way anywhere in the control learning and controls literature is how do you find the dimension of the state space. This is sometimes called the Macmillan degree in control theory. So a lot of the classic system identification results will also tell you how to find n. So of course, those are obtained by the rank of a certain Hankel matrices stabilizing. That thing, how that will perform in the non-asymptotic regime, etc., is not known. Okay. All right, so that's all I have by way of my talk. So hope it was not terribly confusing and hopefully at least nominally interesting. Thank you.
Ramanyam?
Hello, am I
Yes.
audible? Sorry, I was late for the introduction of Professor Viswanath Ramakrishna, who is a distinguished student from IIT Madras. He has given a very nice, though technical presentation of his latest work on control theory, rather stochastic control. And I'm sure that it will be of great interest to engineers and those working in deep learning and artificial intelligence problems to pursue such algorithms for practical purposes.
Thank you.
I would also like to know, I think Professor Aubin and others have also worked on viability theory and control and all that. What is your comment on viability theory?
First and foremost, I mean, there are people trying to, so viability theory shows up in what are called differential inclusions. Control systems can be viewed as differential inclusions. I don't know whether our proof techniques would directly contribute, would interact in a good way with viability theory. This I'm not sure of. In particular, I'm not an expert in that at all. So I do know that Professor Ben-Susan knows a lot about viability theory. He worked on, he has written papers on that. And he did not seem to, so what we are doing here is the naivest thing possible. The one thing that you would actually try to do when you try to estimate something which is not well known, which is least squares. And,
yeah, this is very important.
Right.
First of all, when such a new problem is presented, you have
Right.
to go about with simpler models instead of obfuscating with complicated mathematics. And
Sure.
Professor Dasari in the 70s and 80s also used to work on optimization, control. His student, Dr. Angel, had written a basic paper on control systems, etc. My perusal, browsing of those papers was due to my interest in fixed point theorems. Anyway,
Right.
it's a very nice presentation, Professor Viswanath. Congratulations.
Thank you so much.
If anybody is interested, he may raise a question or two. Just a few minutes left.
I see Dr. Watara's hands raised.
Yes,
May
sir.
I ask Professor Viswanath two questions shortly? So the function, the evaluation function is quadratic time function, isn't it?
Right. It's a simple. So the
You told
okay, so
it is not
three
too complex.
so in each case we can
Okay. So is it possible to solve this one by the mathematically? You provided the algorithm, several algorithms. Did you solve it?
yes, we do get we show what I claim we show, that is the J does decrease and the trajectory goes to 0.
So the algorithm, may we apply deep learning of a neural network to solve the problem using a huge data?
That's a good question. So you're asking whether deep learning can be used to solve another deep learning problem. Of course, I don't see why not, but we haven't tried that.
There are a huge number of the applications of this problem format. I think it is quite interesting.
Designing neural networks which will solve this problem. Okay, no, we have not done that, but I don't see why not.
Okay, thank you very much.
Professor Viswanath, there is a
Yes, you
question
ask
in
him.
the chat box.
Sure, let me see. I don't. Who is this?
Professor
Hope
Tan
of
has
addressing
the,
autoregressive modeling
question.
of multi.
Yeah, I suppose. I mean, I don't see why not, because ARMA identification is very closely related to system identification. That's in a certain sense, all the three results are presented today. Ours, De Persis and Benjamin Beck, etc., are identifying A and B. So I don't see why not. But again, I should not. I mean, till you write out the technical details, we don't know what will happen. Okay. Does that answer your question?
Yeah, thank you very much. I understood.
Dr. Tan, issue of P order, what do you mean by that?
Oh, there is a question from P. Pahat.
Patak, yeah, but I don't know what
yes.
you mean to address the issue of P.
Autoregressive order.
If I okay, so I maybe I'm completely going off the wrong end here. The order that you do not know, this is what you're saying, right? The dimension.
Yeah, basically, sorry to interrupt. Basically, it is about identification of the maximum or autoregression order. That has been an issue.
That's a very good question. I already so when I talked about Macmillan degree, I already mentioned that this is in fact not at all an easy problem, and there's very few results. The point is, in the early realization theory, which is how to get from what are called the Markov parameters to determining the order, the order is bigger than equal to certain ranks that you compute. And of course, in practice, what you want is both an upper bound and a lower bound, right? So, so the only one is, pardon me?
Yes, in some of the literatures, I have found that they have addressed this issue in deep learning methods by dilation networks or stacking of the network. So, could you please comment on that? Whether we can?
I'm not aware of that literature. I'm not aware of that literature, but I'd be very surprised if they are able to find. In fact, if you know some, please send that literature to me, because to me this is essentially an open problem. So it depends on what it is that you're using to estimate this order. Okay.
Yes.
So we are measuring known inputs, and we see known outputs, and from that we are trying to estimate what you'd like to estimate the order first, and then the A and the B, right?
Yes.
As far as I know, there is not much known about this, because the main results on This is called the Kalman-Ho algorithm, etc., to finding this A and B. The Macmillan degree is bigger than equal to a certain quantity that you compute from these Markov parameters. And so what you'd like is also to get a lower bound. Okay, so,
Okay, thank you, sir.
and in particular, if the noise, so the only meaningful problem for me in creating a
Close,
OE,
this session.
pardon me?
Professor Subrahmanyam, please close this session.
Okay, all right. Dr. Pathak, I'll be, if you could send some literature to me which addresses this issue, I'd be most obliged. Thank you.
Sure, sir. Your mail ID would be available through this link, sir.
Yeah, it should be Vish, V-I-S-H, at utdallas.edu. Thank you.
Okay, thank you very much, Professor Viswanath.
Everyone, excuse me, I have to, I'm feeling very sleepy. So, so Dr. Gopal, I'm sorry, I might have to miss your talk, but hopefully I'll
no problem. I fully understand. Thank you very much. Great listening to you again.
Thank you. Bye-bye.
All the best, Viswanath. Season's greetings. Thank you for an excellent presentation.
So, and I once again, a great debt to you for not just teaching me mathematics, but introducing FIM to me. Bye.
Bye.